All right, hi everyone. How's it going? We're gonna push on into chapter 7, and chapter 7 of our textbook deals a lot with different techniques of integration. So we're gonna do a lot of integrals, and that's basically the all of this section or chapter is just a bunch of integrals and different types of integrals. And to begin, we start with a new technique of integration. So we had U substitution. And U substitution was it was kind of like the analog to the chain rule of derivatives. The new technique, integration by parts, is the analog to the product rule. And let's see why. So normally, if we took the derivative of a product of two functions, f of x times g of x, we got this formula, right? We got f prime of x, g of x plus f of x times g prime of x. That was the product rule. And now we're going to do our favorite trick, where the favorite trick that we have done a lot now is where we take the integral of both sides. And notice that it cancels out here. So it canceling out here means that, and I'll write this as the left-hand side, is now that the integral of f prime g of x plus f of x g prime, that is equal to just f of x times g of x. Okay, and now we're going to subtract, right, this integral can go to both ones. So we're going to write this plus the integral here. So that one integral splits on the plus sign to two different integrals. And technically I need to put a new dx here. And then what we're going to do is we're going to subtract this over to the other side to get this interesting formula. And this is the formula that's going to help us define the technique of integration by parts. So notice that first you start out with f prime, and then g is alone. But on the other side, you toss the derivative onto g now, and you just recover f. So the two things that we don't know in this formula, so for example, when you first give an integral, you want to think about it in this form. It's some integral, and you're going to say that, okay, one function is the derivative of one function, of a certain function that I know, and the other one is just the bare one. So we know f prime and g, so the things that we actually don't know we need to find are essentially are this. You don't know this, but you can get it. And you also don't know g prime, but you can also get it. You can get these two things you don't know. How do you get, if you know f prime, how do you get f? Well, you take its integral. And if you know g, how do you get g prime? You take its derivative. So the interesting way that, or I guess the conventional way that this is written, is because this is the derivative of something, you call this guy dv. And then you call this guy u. So if f prime of x is equal to dv, then when you take the integral of both sides, what do you get? Well, the integral of f prime just reduces to f, so this just gives you f. And the integral of v will just be v. So you get that f is equal to v. So now this becomes v on this side. this is still u. And then, again, f is v. And then now we need to figure out what g prime is. So g is u. So g of x, u equals g of x. And so if you take the derivative of both sides, that means that u prime is g prime of x dx. And then we're actually going to call u prime instead in the differential form that we're used to is du. So we're going to have du equals g prime dx. So g prime dx is actually du. And now this gives the form of the integration by parts that we see very frequently. And once we do an example, this will become very elucidated. But the idea here now is if you have the integral of u dv, this is the same as, we're just going to write uv instead of vu, u times v, v times u, same thing, minus the integral of v du. This is the integration by parts formula. Okay, and now let's see this thing in action. So let's say that we want to find the integral of x times the sine of x. Okay. So if you remember in our process, one of these functions we're going to integrate and the other function we're going to differentiate. Those are the two things we have to do. We're going to have to integrate one and differentiate the other. So you have to think about, first off, can you do this? So normally differentiating stuff is not hard, but we can't always take the integral of something. So that already kind of puts a constraint on what we can do. And second of all, you want to make sure that this new resulting integral is actually one that you can solve. So what we're going to do is we're going to say that u is equal to x. And remember, u is known and dv is known. These are the two known things. But to turn u into du, we take its derivative. So this tells us that du is dx. Okay? So we know what du is now. It's just straight dx. And now, the other thing that we're going to say is we also know dv. So we're going to say that dv is sine x. And how do you turn something that's been differentiated into something that's not, is you take the integral of both sides. So when you integrate both sides, this just becomes v, and this becomes the integral of sine. So this tells us that v is the integral of sine x dx, which we know to be negative cosine. So this is negative cosine x. Okay, so these are the two new things that we found. So using our integration by parts formula, we now know that this integral is the same as u times v, so x times negative cosine x, which gives us negative x cosine x, minus the integral of v, negative cosine x, du, which is just dx. So we're just making the appropriate substitutions here. And then notice this minus sign floating out here, we'll just turn this to a plus, and we'll be left with this. Now what's really nice about this is we are left with something that we can actually take the integral of. In this case, it worked out really well. We know how to take the integral of this. So if we push on, this just ends up being negative x cosine x plus sine x plus c. And this is the final answer. So integration by parts allowed us to rewrite this integral, an integral of u times dv, in the form uv minus the integral of v du. So, and then we just cranked it out from there. And now we should make sure that this actually works. So if we take the derivative of this, we should recover x sine x back. So if you take the derivative of that, first you'd use the product rule on this. So the derivative of negative x would be negative 1, and then cosine x just comes along. And then you add that to negative x times the derivative of cosine x, which is negative sine x. And then the derivative of sine is cosine, and the derivative of c is 0. Now notice that this negative cosine x and that cosine x will cancel, and negative x times negative sine x will just give us what we had. So very good, this works. Now another thing to note is, you may be asking, well, why couldn't you have done the opposite? We can take the derivative or the integral of both of these functions, so why didn't you do the other one? So let's see what happens when you do try that. So now let's say we let u instead be sine x. This would imply that du is cosine x dx. Okay, so we have that. And then if we let dv be x, once we take the integral, we would get that v is 1/2 x squared. So now let's see what the integration by parts formula would give us. It's not wrong, it just may be really hard to deal with this outcome. So we get u times v, so 1/2 sine x time, or 1/2 x squared sine x, minus now the integral of v, 1/2 x squared. Du though is cosine x dx. Now this integral here is even harder than the integral we started with. This one we don't know how to do. U substitution won't work, and all the other techniques that we know will not work here. So this is why the first choice was better. It actually allowed us to do a calculation and not get stuck again. So there's a little bit of there's a finesse to this that will be developed over time once you practice. Okay, now let's keep going and do another example. I'm just going to keep this up here. Okay, now let's say that we want to find the integral of ln x. So say we want to find this. And now you may be wondering, well, there's not two functions there. Like, don't you need a u and a dv? And at first it doesn't look like it's there. But notice that you can think of this as the integral of 1 times the ln of x. So now another function magically appeared, which is 1. So now we're going to pick our u and our dv. So remember, whatever dv becomes, we end up integrating it to get v. So if I pick dv as ln, that's going to be very bad because the integral of ln is the thing I'm trying to find out. We don't know what that is at this point. So that's a very bad choice. So we're going to let dv be 1. So dv just equals 1, meaning when you integrate both sides, v will just be equal to x. Right, the integral of 1 dx is the same as the integral of 1 times x to the 0 dx. And then if you use the power rule, this is 1 times x to the 0 plus 1 over 0 plus 1, which is 1 times x to the first, which is just x. So yes, doing all that work, remember, you just get x out of this. And then now the choice of v is pretty clear. We're going to let v be ln x. And this means when we take the derivative, dv will be 1 over x dx. Okay, and now let's crank this into the integration by parts formula. So according to the formula, the integral of ln x dx is u times v. So this should be a u. I am so sorry. Maybe that was confusing, my bad. This should be a u. U is this, so du is that. Hopefully that clears things up a little more. Okay. So we get u times v, which is x times the ln of x, minus the integral of now v, which is x, times du, which is 1 over x dx. And oh, that's really nice. Because what happens with these is they just cancel out to give you 1. And we already know what this integral is, it's x. So final answer is this. So that's very cool. The derivative of just ln x, which we didn't know before, actually turns out to be this. And then of course I forgot the plus c. But that's pretty interesting how sometimes it seems like it's not going to work, but if you think about there being a 1 here, then there really are 2 functions. So that's the key there. Okay, and now we can do some examples where we need to apply the integration by parts formula multiple times, so more than once, before we can stop. Okay, so let's see an example of this. Let's say we want to find this. Okay. And then, in this case, you may be thinking, okay, now, again, what choice do I make? What is u and what is dv? But if you remember, we end up taking the integral of v du. And this t squared, if the t squared weren't there, we know how to take this integral. So we want to somehow effectively kill off this t squared or make it into a constant. And notice if we take its derivative once, we get 2t. Take the derivative again, we get 2. And so then if we're just left with 2 times, whatever we get for the rest of it, though, we will be able to take the integral. And so that is a good indication as what to use for u and dv. So we're going to say u is t squared, which means du is 2t dt. And then the guy that we're integrating, dv is e to the t. Well, if you integrate this, you get v is, what's the integral of e to the t? It's itself. Okay. So now applying the integration by parts formula, this is going to be u times v, so t squared e to the t, minus the integral of v e to the t times du. So times 2t dt, which I'll float this out in front. So 2t e to the t dt. Okay. Now, this new integral we actually cannot do again. U substitution will not help us. The only real choice is let u be t here or let u be 2t, but neither one of these fixes the problem. And so we're going to apply integration by parts again to this. So what we're going to do instead now is, let's make a note of this, is that the integral here is t squared e to the t minus this integral. But we're going to use integration by parts to figure out what this integral is. Okay? And now again, the choice of u and dv is clear from the last time. We're going to let u be 2t, take the derivative, says du is 2 dt, and then let dv be e to the t, and this says that v is e to the t. Okay, so then following this thing here, we have the integral here is equal to, okay, u times v, so 2t e to the t minus the integral of v du, and this 2 is e to the t times 2. I'll just write it as 2 e to the t. And this is beautiful because at this stage we do know how to take this integral. The constant just floats out in front, and our favorite integral is the integral of e to the t because it's itself. So when the dust clears, this is 2t e to the t minus 2 e to the t, which we can now make this substitution. So we figured out what this integral is. So the original integral that we were trying to find, we can go back to that, is now this is minus the thing we just found, 2t e to the t minus 2 e to the t, and then, plus c as usual. So then we get the integral of the thing that we want is, okay, t squared e to the t, distribute the minus sign, minus 2t e to the t plus 2 e to the t plus c. And then nothing combines, and so this is the final answer. So yes, sometimes you may have to apply the integration by parts formula repeatedly, multiple times. So that's pretty cool. Okay, and then now let's do another example. Let's find the integral. Oh, and I erased the formula, I'm so sorry. We said the integral of u dv was uv minus this. So that's the integration by parts formula. And what we're interested in now is the integral, much darker, e to the x sine x. So this is the integral that we want. And now here, it's kind of tough to make your choice of u and dv, because both of these functions, when you take their integral or you take their derivative, we know how to do that. But they end up kind of just giving you something similar. Like the integral and derivative of this is itself, but the integral or derivative of this is, related to cosine. So it kind of seems like it's going to push this into a more perpetually worse state. But let's just stick with it for a second. Let's see what happens if we kind of just go with our gut and kind of just pick some stuff. So what we're going to do is we're going to let u be e to the x, and that means when you take the derivative, du is e to the x dx. And then we're going to let dv be sine x. And then so when you take the integral, v will just be cosine x. Oh, sorry, negative cosine x. Right, the integral of sine is negative cosine. Okay, so then, yes, this doesn't look like it's going to help much, but just hang with me for a second. And once you see this trick once, you'll know to do it again. It'll be in the back of your head. So the integration by parts formula would tell me that this, what we started with, is u times v, so negative e to the x cosine of x, now minus the integral of v, negative cosine x, times du, e to the x dx. Now this minus sign I'll float out to turn this into a plus. And then cosine x times e to the x, I'll just write it as e to the x cosine x instead. The order you multiply things doesn't matter. Now this again doesn't look the best, but we can apply integration by parts in a very similar way here to this guy, using almost an identical choice of u and dv. So applying integration by parts again, in some sense, technically, you have to use new letters, but if in the back of your head you keep in mind that, like, oh, this is like the new u and the new v, you can be a little careless and less formal and still do it that way. So here we're going to now say the new u, which I guess you can call u prime, may not be good, but we'll just stick with u, is e to the x. Then that would mean that du is again e to the x. We've already seen this. And then maybe let me make a note of this up here like we did last time. So this we saw with one application of integration by parts gave us this. And we're using integration by parts on this now. So yeah, we're going to let u be e to the x, and dv we're going to let be cosine x. Meaning that v is the integral of cosine, which is sine x. Okay, so then integration by parts would tell us that this is uv e to the x sine x minus the integral of v du. So sine x, oh, and I forgot to tack on this dx here, so sorry. Sine x times e to the x dx, which again, we can just flip the order that we write this and write e to the x sine x. And now something very interesting happened. This was the integral that we were trying to get in the beginning. So now let's make the substitution. This guy is the same as that, and let's replace it with what we found. So this guy is actually e to the x sine x minus the integral of this. And now this is an extremely complicated case of this, but notice that these are just like terms, right? This is like I have x equals y, this being y, plus z, this being z, minus x, this being x. So you can just add it over to get 2x equals y plus z. So if you add the integral over, this entire expression over, you would get twice the integral is equal to, and now I'll write this as e to the x sine x minus e to the x cosine x. And now this is amazing. Once we divide by 2, we actually have a formula for what we were looking for, and that's going to be the answer. So when you divide by 2, aka multiply both things by 1/2, and then tack on the c, we have our final answer. So that's really neat. You actually were able to algebraically solve for the answer that we were looking for. So that's really, really crazy. That's whoever came up with that trick at first is very, very clever. Now the next thing that we want to address is, you may be wondering, well, you only had this for indefinite integrals. What happens when you tack on, when you want this to be a definite integral with limits of integration? So what happens is, this UV, this product, you end up evaluating that product from A to B, and then you just take this integral as a definite integral from A to B. So that's the integration by parts formula if you have limits of integration. So let's see an example of this. So let's say we want to find the integral from 0 to 1 of tangent inverse x. Okay. And then some maybe nice formulas to remember were the derivative of tangent inverse was 1 over 1 plus x squared. And so consequently the integral of 1 over 1 plus x squared was tangent inverse. So these might be two nice formulas to remember for this problem. Okay, so the limits of integration aren't too scary. We know how to deal with them. And so we just need to figure out what u and dv are, which again, because there only looks like there's one function here, you can really think of this as 1 times tangent inverse x dx. And now it's very clear which of these we want to integrate and which of these we want to differentiate. We don't want to integrate tangent inverse because we don't know its integral. That's the thing we're trying to find, right? If we knew this integral, we wouldn't have to resort to this technique. So it's very clear that we're going to let dv be 1, so we can integrate this, and we're going to let u be that, so we can take its derivative. We do know its derivative. So we're going to let u be tangent inverse, meaning that du is 1 over 1 plus x squared dx. And then v, we're going to let be 1, basically. And that, or sorry, dv. dv is going to be 1, and so when you take its integral, v will actually be x. Okay? And now let's apply the integration by parts formula with 4 definite integrals, with limits of integration. So this would end up being u times v, so x tangent inverse x, evaluated, because we have an a and a b, from 0 to 1, minus the integral from 0 to 1 of v, which is x, times du, which is 1 over 1 plus x squared dx. Which, if you simplify this, is x over 1 plus x squared. Okay, so that's pretty cool. We're getting some really cool looking stuff. So now, if we move this up here, we would have the thing we're looking for is equal to all of this. So let's simplify this. So evaluation from 0 to 1 means stick 1 into this and subtract it from when you stick 0 into it. So this will be 1 times the tangent inverse of 1 minus 0 times the tangent inverse of 0. That's what all of these symbols collectively will end up being equal to. Well, this guy doesn't amount to anything. 0 times anything is 0. So we really only get this. And 1 times anything is itself. So this is really just tangent inverse of 1 minus the integral of x over 1 plus x squared dx. And now to deal with this integral here, we're going to use u substitution. So we're just hammering on all these integral techniques that we're learning. So this is pretty crazy. And because we used u earlier, again, technically you don't want to use u again because that variable has already been, used. But if you're just careful and you're not sloppy, you can use it again. But might as well just try something else. So instead of u substitution, let's try m substitution. So we're going to let m be 1 plus x squared. So then dm will be 2x dx, and then dm over 2x will be dx. So that'll help us take this integral. So okay, what we have will end up being equal to, what's tangent inverse of 1? It's pi over 4, right? If tangent inverse of 1 is equal to some number x, this is the same as asking tangent of x equals 1. So the tangent of what angle equals 1, but remember that x, the angle x that you're answering this, has to lie in the appropriate range of the inverse tangent function, which is this. So what angle between negative pi over 2 and positive pi over 2 gives you a tangent of 1? Well, it's pi over 4. So it's pi over 4. And another way to think about that is, remember with our little circle diagrams, is if you remember from trig, if you stick tangent of pi over 4, if you stick pi over 4 into the tangent function, you get 1. Meaning, if you stick 1 into the inverse tangent function, you should get pi over 4. These are just different ways of thinking about all of this. Okay, so long story short, this is pi over 4. And then this becomes minus, and this should have limits of integration from 0 to 1. But when I'm rewriting it, I'm going to omit them for a second because I haven't worked out what they should be. So let me just do that on the side. So m of 0, the new limit of integration will be 1 plus 0 squared, which is 1. And m of 1 will be 1 plus 1 squared, which is 2. So those are my new limits of integration. So this would be minus the integral from 1 to 2 of x over u. All of this is u. And then dx is dm over 2x. And so notice this x cancels, which is exactly what I wanted. Okay, and then so now we have pi over 4 minus integral of 1 to 2, and this dividing by 2 I'll float out as multiplying by 1/2. Oh, I'm sorry, this should be m. 1. Sorry, see, I've used u so many times that I called it u, but it should be m. We picked m to be that. So we get 1 over m dm, and that's going to be equal to pi over 4 minus, well, what's the integral of 1 over something? It's the ln of absolute value of that. So it becomes 1/2 ln absolute value of m. Evaluate that now from 1 to 2. So So now this is pi over 4 minus, and I'll put a big parentheses around this, because this minus sign is going to multiply the final answer. And I'll put the 1/2 actually here as well. So minus 1/2 times the ln of 2 minus the ln of 1. Right, if you take the absolute value of each of these, you just get 2 and 1 back. Okay, what's really nice is the ln of 1 is actually 0. The ln of 1 is 0. So really, when the dust clears, the final answer is pi over 4 minus 1/2 ln 2. And that's the value of this definite integral. So the integral from 0 to 1 of tangent inverse is equal to that. And so we had to use both integration by parts and use substitution to do this. So this is starting to get kind of lengthy, but expect more lengthy problems to come. What's interesting about math is the notion of what is lengthy and what is not lengthy changes over time. At first, you thought that solving for a few variables was lengthy, or solving the quadratic equation, using the quadratic formula was lengthy. Now this seems lengthy, but that'll get redefined even more. So over time you kind of get a little jaded and things don't become as lengthy anymore, unless they're really, 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 really long. Okay, so let's do one more example of the definite integral. I like those. I'm just looking at the book for something nice. Let's see, something not too long. Okay, let's do this one. This is number 24 from this section. And it's the integral from 0 to 1 of x squared plus 1 times e to the minus x dx. Okay. So what we're going to do is, again, we kind of know pretty much right off the bat from our experience now that we're going to want to take the derivative of this guy. Because the more we take its derivative, it basically will end up becoming a constant, which is good. That is something, a constant times e to the minus x, we can take its integral. So that's where we want to go with this. So we're going to let u be x squared plus 1, and that means that du is 2x dx. And we're going to let dv be just e to the minus x. And now you may be asking yourself, what's the integral of e to the minus x? And we'll just do that off to the side. So the integral of e to the minus x can be done with a very quick u substitution. You let u be minus x. So then du is negative dx. And so when you toss the minus sign to the other side, this is what we get. To interchange dx with du, you just pick up a minus sign. So this becomes a minus sign here, and then e to the u du. So this is negative e to the u plus c, which is negative e to the negative x plus c. So it's the same as e to the x, you just pick up a minus sign in front. And these really quick little u substitutions we're going to do pretty frequently. They're going to start popping up like crazy. So we're going to want to get used to them. So then v is going to be negative e to the negative x Okay, so then according to the integration by parts formula, I take u times v, so this becomes equal to negative e to the negative x times x squared plus 1, evaluated from 0 to 1, minus the integral of v, negative e to the negative x, times du, so times 2x dx. Now this minus sign and that minus sign collide to give a plus, and then the 2x I'll write out in front. So 2x e to the negative x, and this is from 0 to 1 as well. And notice that we will have to do integration by parts again. But let's figure out what this is real quick. So let's do this on the side so that we just have it and we don't keep writing it. So if you plug 1 into here, you get negative e to the minus 1 times 1 squared plus 1, which is this. So that effectively gives negative 2 times e to the minus 1. Negative 2 times e to the minus 1. And then you subtract that from negative e to the 0 times 0 squared plus 1, which is just 1. And then e to the 0 is also 1. So negative 1 times 1, that's effectively just negative 1. And then so you have negative 2 e to the minus 1 plus 1, effectively. Once the dust clears, all of this is equal to that. Okay, so then this is, let's just rewrite it, negative 2 e to the minus 1 plus 1 plus the integral from 0 to 1 of this. Okay, and now let's do integration by parts again. And our choice of u and dv is going to be very quick again. So u will let be 2x, which is nice because now finally it's just 2. No more x's involved. So 2 dx. And dv will be the same thing as last time. So v will be negative e to the minus x, the integral of this, which we already did last time. So then we get, negative 2e to the minus 1 plus 1 plus now, again, the uv thing. So uv, so plus 2x times negative e to the minus x. But we evaluate that from 0 to 1, remember. Minus now the integral of v, negative e to the negative x, times du, which is 2 dx. And now again, this negative and that negative give us a plus, and this 2 will float out in front to just get this. Oh, and this is very nice. This is beautiful. Now we know how to take that integral very quickly. Okay. So then coming up here, this guy has been just coming along for the ride. So this was already there. And now evaluation of this from 0 to 1, let's do this off to the side. It'll be 2 times 1, or let's simplify this for a second. This minus sign here will just float there. So this is negative 2x e to the negative x. So this will be negative 2 times 1 times e to the minus 1 minus negative 2 times 0 e to the 0. And now you can see that here there won't be any contribution. when you stick in the 0, it's gone. So all that we're really getting is negative 2 e to the negative 1 out of this. So now again you have minus 2 e to the minus 1 and then plus 2, and then we know this integral, right? The integral of e to the negative x is negative e to the negative x. So this becomes 2 times negative e to the negative x, which again, when you combine this, is minus 2 e to the negative x. Then we evaluate that from 0 to 1. So yes, a lot of evaluations. So the first one we did came from that. Evaluating this from 0 to 1 gave this. And then taking this integral, giving us this, and the limits of integration from 0 to 1 tells us to evaluate our integral from 0 to 1 now. Okay, so then this becomes, these are like terms, right? So this is like a negative 2x minus a 2x, which gives us a negative 4x essentially. So these combine to give negative 4 e to the negative 1 plus 1, and then minus 2 times, so we'll pull the minus 2 out and just stick the 1 and the 0 into e to the minus x. E to the negative 1 minus e to the negative 0, which is just e to the 0. Okay, so then this becomes negative 4 e to the minus 1 plus 1 minus 2 e to the negative 1, and then e to the 0 is just 1, right? So negative 2 times this negative 1 gives us a plus 2. So then when everything combines, the minus 4 minus the 2 gives us a negative 6 e to the minus 1, and then the 1 plus 2 gives us a plus 3. And that is the integral of this guy. Okay, so there's a lot of steps there, but hopefully it makes sense, and of course you can feel free to ask me in class, but hopefully at least the idea makes sense. How we used integration by parts twice, and because of that we had to do that evaluation formula twice. We evaluate from 0 to 1 and stuff like that. Okay, so very good. I think this is a good stopping point. Doing another example would probably take too much time, but hopefully these ideas make sense, and please feel free to ask me in class. I'll see you guys next time.